Welcome to lecture 65. We are still on Pauling's rules number 1 because there's a lot in that first statement. We got to talk about coordination number. We got to talk about the radius of ions and the ratio of those radii and how that affects the potential compounds. Or that's what Pauling's rules say. Anyway, we're gonna get into that this class and then. Partly, once we understand coordination numbers completely, remember we're still just looking at kind of individual atoms. We haven't put them together yet. To put them together, we're going to say, well, what's the relationship between coordination number and composition? It's pretty straightforward. You know it probably intrinsically, but we kind of just want to prove it. And then you have everything, because now we could say, all right, here's a chemical compound with the ratio of A to B. That means we have this coordination number. That means that here's the choices. Here's the polyhedron it has to be around these atoms, and then if that's the case, here's all the space groups that it could occupy. Okay, so that's what we're after, and then we'll go into other Pauling's rules after that, which are help define other choices we have to make further down the line, but number 1 really defines quite a bit here. So just a quick review of number 1. We talked about what a coordination polyhedra is. That's if I look at AB. A is bonded to B. The number of B's that it's bonded to is a coordination number. And we talked about their radius ratio has limitations because of pure geometry. And both, thinking about cation ions, we're thinking about ions, help in Pauling's rules as well as this sort of hardball radius ratio thing, right? So everything is focusing for ionic bonds here because it's a little bit easier to understand than we get into covalence. So we're almost there. Just have to do a little bit more work. Reviewing what we did last time, we had already made a list here. Oops, sorry. We had already created a, I'll show you in a minute, CNA. We went through how if we have the triangular case or the tetrahedral case, and so on. And we talked about there was a limit of 0.155. You can see them here because when you're referring to RB over RA, it's the same as that. It's a 0.155, et cetera, et cetera, et cetera. But we mentioned last time that we want to convert into RA over RB, which just requires a manipulation of the less than formula. But it's not obvious unless you go through that. And we kind of showed that if we now write the coordination limitations, the limitations from the coordination number of around B, we have in terms of RA over RB, so that we can relate them to each other, we now have these expressions over here. So to summarize in a complete table, this is what I was just talking about, that we have the C and A part, and we've got the C and B part, but now they're both in terms of RA over RB. That's what I put in here. Now we can do an AND. We have restrictions from C and A and C and B, and this little table allows us to do everything. So for example, we already gave you the case where let's imagine that we wanted to have coordination for A and B both be 3, and we said, the conclusion there is that you have to be greater than RA over RB. Remember, everything's in terms of RA over RB now. RA over RB has to be greater than 0.155, but less than 6.45, right? So pretty wide range actually. But you can see here, if I kept the same thing, 12 to 12, basically you'd have to have RA over RB be identically 1, and even there it's probably iffy. So basically, if you tried to have A and B have exactly the same coordination. You'd have to have them be exactly the same size, and then it's still questionable. Let's back off a little bit and say, well, let's look at 8 and 8, and you can see that, yes, it actually opens up in that you would have the ability to fit in a fairly narrow range, but you can imagine, all right, are there some ionized, so you have to look, far enough apart on the periodic table so they're not covalent bonds, but in this hard bond kind of limitation where they're billiard balls attracted by purely Coulombic forces, you'd say, all right, I can find probably some ratios of ions here where, I could get a coordination of 8 around each. Again, it's going to be kind of rare, but I might be able to find that. And of course, I don't have to do it that way. I would say, well, I could look, for example, across, and I could say, well, what about if I had a coordination of, 4 and 8? Just make this up, right? Well, if I want to do 4 and 8, then I would have to have RA over RB would have to be greater than 0.225, but less than 1.37. So a fairly narrow range, but not impossible. So I could have A have a coordination number of 4, and I could have B have a coordination number of 8. Now you'd have to think about, well, how can these be arranged? One wants a tetrahedral site, one wants an octahedral site. But there are structures which do that. So now how do I think about that in terms of composition? Isn't that sort of the same, if you think about it, as 2 and 4? So here I'm saying, well, A, I want to have a bond at every 2 atoms, and B is twice as many bondings, right? Here, same thing. A and B has twice as many bondings. So you would think that those would be a similar composition. So this should motivate a discussion then of how are coordination numbers related to composition. And so that's what we're going to just quickly do here. I think some of you, this may be, somewhat obvious, but I think it's worth doing. So let's picture a B atom. And it has it's sharing itself with C and B A atoms. So what you could say is that the fraction of B connected to an A atom is equal to 1 over C and B, where 1 is the full atom. So you just take B divided by C and B. You could say, okay, it's the charge, whatever, but we'll just call it a B atom, a 1 B atom divided by C and B. So in other words, if I share this 1 with 2 A atoms, right, coordination number is 2, and therefore 50% of B is shared with 1 A atom, and 50% of B is shared with another A atom. Now let's consider atom A, and you would say, all right, it's connected, and it has some C and A. And so same thing here, fraction of A connected to B atoms is 1 over C and A. So with the realization that 1 over is the fraction of B in a bond, then 1 over, so let's just write this out. So the realization that 1 over C and B is fraction of B in a bond, and 1 over C and A is a fraction of A in a bond. And since all bonds are representing the composition of the solid, because each bond on average, these are averages, right? Then you end up with the total. So if we look, these fractions may not be whole numbers, so we have to normalize. So a total fraction between A and B is 1 over C and B plus 1 over C and A, which is C and B plus C and A over C and B, C and A, right? So now if we just want to look and say, aha, the composition of A is, and you can see here how whatever fraction we're talking about from an A perspective, when this flips over, it actually cancels this one. And that's why you end up with running out of pixelization. But essentially C and B. So, and then XB would be the same. So now if I were to write a chemical formula, I would say A would have C and B over C and B plus C and A. B, C and A over C and A plus C and B. And sometimes you do see this, for example, a lot in semiconductors when you have, pure alloys, you'll see some sort of ratio like that. You might say, A 0.3, B 0.7 or something if they were in the same site, adding up to 1 or something. But equivalently, you can drop the fractionalization. They're both referenced to the same frame, and the chemical formulas are just the ratios, right? So essentially this means that you can write, and that's the convention, and now you can see why it's inverted. If we look at a general composition A, B, M, right, then you realize that C and A to C and B is M to N. So a quick little example is if I have, A to B, right? It means that C and A to C and B equals 1 to 2. So the coordination of B is higher. And you can see that, of course, in this formula because there's more A's around, and so there obviously must be more A's bonded to B. And so that is the relationship between the coordination ratio and the composition ratio. So now let's apply that to some examples. AB compounds. So remember, the key thing here is that this has a 1 and this has a 1. Actually, let me change the color. It's implied because we don't write it, but it's one. They have to be right. So CNA to CNB is 1 to 1. But remember, it could be 2 to 2, could be 3 to 3, could be 4 to 4, 6 to 6, 8 to 8, 12 to 12. That's a little tricky thing, which is that we only have the relative ratio, but we actually don't know what the exact coordination is in each case. So of course, if it's just 1 to 1, then basically there's no restriction on RA or RB. Same thing with 2 to 2. Still no restriction because they could be all in a line. Of course, once we go to needing to have 3 on each side, so B has to be coordinated 3 and A has to be coordinated 3. We already gave that example to you before in another lecture where now the RA over RB has to be between 0.155 and 6.45. So pretty wide window, but nonetheless, not everything is going to be able to have that. And this would be a different structure, don't forget. I would have threefold. I would have a coordination of 3 around each atom. I have 3 bonds and 3 bonds, right? Now, if I have the right size atoms of A and B, it may be that I have tetragonal pockets, and the choices are smaller there, but each one might be in a tetragonal window. And of course, that's very famous. It turns out that more covalent materials also have this same kind of setup, but something like zinc sulfide, which is still a very ionic bond, you find out that it forms a zinc blend structure, and the zinc blend structure is essentially just 2 interpenetrating cubic FCC lattices. So you can see here that the sulfurs are drawn in the blue. They're essentially 1 FCC. And then shifted from it 1 quarter, 1 quarter, 1 quarter is where the zinc goes. So the way to think about this is this zinc and this zinc are on a diagonal going across here, right? They're on a diagonal going that way. Where up in the next 3 quarters of the cell, there's a line connecting these guys the same way, but it's rotated 90 degrees, right? And so these, I just draw that to show you that, if you drew a line through here, you can think of this as rotating. This is that, and then it rotates up in the next thing. So, but more importantly, you can see how each one is coordinated environment, where here you can see the zinc is clearly bonded in this tetrahedral site. It's got 4, it's got kind of 2, hold on. It's got 2 bonds coming up this way, right, kind of going in and up out of the plane to something closer to the plane. I've got these 2 guys here, so it's in that little tetrahedron. And of course, these are completely equivalent, so I could have switched these labels or, shift up by a quarter, and I would see that the sulfur ion is also in the same kind of environment. And so those are tetrahedral holes, and this is called a zinc blend structure, of course, for obvious reasons. The other case is that if I go up and I say, aha, now I can possibly have an AB compound with 6, coordination number of 6 in each one. That's the famous sodium chloride structure. So this one is the zinc blend, as it's called. Same as diamond. It's a diamond. All the atoms are the same. And this one is, of course, the sodium chloride structure. And you can see here that if I were to call this one, either one, let's say it's a sodium, then let's see, sodium. Yeah, this would be sodium because it's smaller the way it's drawn than than these guys. And you can see here it's bonded 1, 2, 3, 4, 5, 6, and the same thing for the other ones, right? Which is why we have this kind of structure. And you can see that as you go up, it gets increasingly difficult to have both A and B be the same composition, and in all an octahedral site, it's not impossible, but that's the cesium chloride actually achieves that. And of course, we end up with very difficult to have 12 and 12. So now if we go to an AB2 compound, so now we have twice as many B atoms as A atoms, right? And that means that the coordination around A has to be much higher, right? There's more B's, so A has to be bonded to more B's. And you see that here. Now again, all it is the ratio of 2 to 1. It could be 4 to 2. It could be 6 to 3. It could be 8 to 4, 12 to 6, right? And so, again, not too many restrictions until you get up to 6 to 3, right? Then they're still pretty wide and still pretty wide. So actually something that opens you up to much higher coordination is not having A and B be the same composition. If I shift composition now, I can actually have a chance even at 12 to 6. But of course, that's because I'm reducing the coordination on one of the atoms. I'm not having 12-12 here, right? It's 12-6. An example of a compound here is calcium fluoride, where I am able to have one atom be bonded. So let me show you this one here. They're kind of showing you this in the two little sub-polyhedrons that are drawn here. Here is an atom that is bonded to 1, 2, 3, 4, 5, 6, 7, 8, showing you how it's bonded to 8. And so that's the calcium. So this guy is calcium. And then this is showing you the green one, which is the fluorine. And I like this a lot because it shows you how that one is also, it's bonded in a tetrahedron, you see. So it's bonded to 4. And that's the fluorine. So this is the fluorine in here. It's bonded to these 4 atoms there. And you can see how it fits into the cubic. It's in a cubic crystal structure that is face-centered with the calcium, right? But we have the fluorines taking these tetrahedral holes. So I have 8 of the, 1, 2, 3, 4, 5, 6, 7, 8. Yes, 8 of them inside. And the way you probably remember how you can calculate this is all 8, those tetrahedral sites that are being filled. So I have 8 full fluorine atoms, right? Now the calcium one is a little bit more, you got to take the fact that that they're all shared, right? So on a single face, what do I have? On a single face, I have a face-centered one, right, which is a half atom, right? And then I have the 4 corners. Each corner is shared by 8 cells, right? Don't forget. So I have 4 atoms on a face. And they're each shared by 8. Now the way to add this up is, if I look at this whole cell together, I have 1, 2, 3, 4, 5, 6, 7, 8. So I have a total of 8 corners, right? And so I have 8 corner atoms that are shared each with 8. And if I look at the faces, I have 1, 2, 3, 4, 5, 6 faces. So I have 6 faces that are each shared with 2, right? So when I look at that, right, I can see that I'm going to have 3 atoms from the faces plus 1 from the corners. And so there's 4 calcium. So of course that means that there's twice as many fluorine atoms. Everything works out the way it should. So again, the way you would use this is you would say, I have a certain ratio of my A ion to my B ion. Let's see which ones it can fit into. And then use the other rule sometimes, which you haven't gotten to yet, to understand how to further decide where to go. Then, of course, we could look at the A2B case. Really just the inverse of the last one, where there's more A ions, just to put in your mind that, of course, that's completely possible. And you can see that in this copper oxide structure, where there's many, many more copper ions. So these are the copper, and they're only bonded, each one is only bonded to 2 other guys, right? You can see that here the coordination number is 2 for copper, and then oxygen has 4, and so you can see the oxygen is clearly this one because it's bonded to these guys. What this means is that this copper is only bonded to one other. In the next cell, this is only bonded to one other oxygen, right? So lots and lots of copper around with a few oxygens inserted in only 2 of the tetrahedral sites in this cubic structure. And so on. I think you get the idea. Finally, there's more complex ones as we go up. Here is a A2B3. Now we take the ratio here and we say, now there's a 3:2. If it's 3:2, there's no problem here, but if it's actually coordination of 6 and 4, I am restricted. And an example of that is Al2O3, which is a little bit difficult to see, but there's a couple ways. This is just showing you the kind of taking out the polyhedron that the aluminum sits in, and it's showing you that it's in this site where we have 6, 1, 2, 3, 4, 5, 6 oxygen atoms around it, confirming the coordination number of 6 for the aluminum. What's a little bit harder to see, of course, because we didn't draw it in, and I'll get to that in a second, is the tetrahedral coordination for the oxygen. Now, of course, corundum or alumina or sapphire is key because you can replace some of the aluminum with transitional metals, and of course it's like ruby crystal laser has some chromium impurities inside there, and because of the D shells and the fact that it's fairly isolated in this little pocket, you tend to get a small amount of crystal field splitting, and you can use that for the original chromium red laser, solid state laser that was fabricated in the 60s. But the over here is a complete structure, and it's a little bit more difficult to see. One thing that you'll notice is that this is a Wurtzite structure, and it has a close packed direction, which you can kind of see here. There's like layers of the 2 different elements tightly grouped, and then there's a bigger space, and then you have another set, and that's because the stacking that happens is the high density direction, which is in Wurtzite. That's the 0001, if you were to use that kind of indexing. And so that's a quick review of how atoms can be thought about as we insert them in using Pauling's first rule, and we'll continue with this other ones in the next lectures.